So thank you, everybody, for coming tonight. I know it's a long day at the AACC, and we appreciate you taking the time to join us for an evening session after a full day of activities and a full week yet to come. I wanted to welcome you today to today's industry workshop that's sponsored by Abbott Diagnostics. My name is Alex Carrillo, and I'm in U.S. Scientific Relations at Abbott Diagnostics, based out of the headquarters in Chicago, Illinois. It's my pleasure to be moderating this evening's workshop titled Sigma Matters, Transforming Lab Quality Using Six Sigma, Informatics, and Moving Averages. We have three distinguished speakers this evening. There will be Sten Westgard, who is Director of Client Services and Technology from Westgard QC, based up in Madison, Wisconsin. Dr. Joe Litten, who is the Corporate Technical and Developmental Manager at Valley Health System in Winchester, Virginia. And Dr. Phillip Bach, who is a clinical chemist for Intermountain Healthcare and adjunct assistant professor of pathology at the University of Utah Medical Center in Salt Lake City. I'll be introducing each speaker prior to the presentation, then following the third and final presentation, we will open it up for some Q&A. So our first speaker this evening is Sten Westgard. He needs no introduction, but we'll introduce him just as well. As I mentioned, he's the Director of Client Services and Technology for Westgard Quality Control, and I've had the pleasure of working with Sten on several Six Sigma symposiums in the past. Now, incidentally, Sten does a lot of travel, and he's been doing a lot recently, as he typically does, including to very hot and dry Saudi Arabia last month during Ramadan. So he made me a promise that after today's session was over, he would enjoy a cold beer with me. So, Sten, I'm going to hold you to it. So for 20 years, Sten has managed the Westgard website, course portal, and blog, creating and administering online training, as well as editing and writing hundreds of reports, essays, and applications on quality control, method validation, Six Sigma risk management, and other laboratory management topics. He has edited and contributed to numerous books on quality, including Basic QC Practices, Basic Method Validation, Six Sigma QC Design and Control, Six Sigma Risk Analysis, CLIA Final Rules, Assuring the Right Quality Right, The Poor Lab's Guide to the Regulations, and Nothing But the Truth About Quality. Sten is also an adjunct faculty member of the Mayo Clinic School of Health Sciences in Rochester, Minnesota. The title of Sten's presentation is Transforming Lab Operations Using Six Sigma. Please welcome Sten to the stage.
All right, thank you very much. I appreciate all the effort that you took to find this level. I think they call it international because the word dungeon is too negative. But I do appreciate the effort, especially after a long day. At least we are in a cool area. I also want to again thank Abbott Diagnostics for holding this session. I want to start by saying I'm really only the warm-up act. I'm the opening round for two distinguished clinical biochemists who have really taken Sigma metrics and then moved it to the next level. So when we talk about Sigma Matters, they're moving it beyond just achieving a certain level of quality, but now thinking about what you do next. What do you do to make sure you can prove that achieving a high level of quality matters to your bottom line, but also how do you make sure that even if you've done some reductions in how you run your QC, you're still going to assure the quality of that result through something like average of normals or moving averages. I also want to acknowledge a particularly distinguished member of our audience. Dr. George Sembrowski is here. He worked with my father several decades ago and did some of the early work on average of normals. And it's been decades since that first publication, and we've been waiting to see it really applied well in the real laboratory operations. And Dr. Phillip Bach will be our final speaker who will be able to present that to us. So again, my talk is going to be about Six Sigma, about achieving that level of quality. And I need to start with a standard disclosure. Abbott has paid for my time and my travel. Without them, I could not be here today. And now many of you have already seen this more important disclosure. This is the one my father mandates. I am only a Westgard. I am not the Westgard. Okay? So for those of you who know the Westgard rules, I ask you, please do not hold that against me. Okay? I am not responsible for the Westgard rules. I grew up under a different set of Westgard rules, all my own. I was under very tight control. But as it turns out, my father found much more success applying rules in the laboratory than he ever did on his children. I now have 2 teenagers, and I'm attempting to develop the second generation of Westgard rules with very little success. But what more important to know about me is I've been working with my father for the last 20 years, trying to help him spread the tools and the techniques to as many labs as possible so that you can put them into action, improve your quality, make it easier for you to operate, and also assure that quality of the right test result. My other job is to work on the Westgard website. So that is, our main website has 45,000 laboratory professional members. This is a free membership. You join and you get access to more than 500 different articles on such things as Westgard rules, QC, method validation, Six Sigma risk analysis, IQCP, ISO 15189. In the center here, you see our course portal where we do structured training. If you want a specific course in Westgard rules, we have a syllabus, we have quizzes, we have a final exam. If you pass that, we will give you continuing education credits. And then finally, we have a blog where we do shorter articles. We cover timely things, something that's happening in the news that's going to impact laboratories, or perhaps a new article that's been published in a journal that's really going to impact your operations and your quality. And finally, we do questions and answers. We like to take the questions that we get from these many thousands of members and not only help the one lab that had the courage to ask the question about the challenge they were facing, but we also answered it in a way so we can help a lot of other labs that are probably facing this same problem but didn't know that they were not alone. And again, all of this is part of what I feel my father said as the mission for our company is to spread these tools and techniques to all the different labs around the world. Now, my specific topic is going to be about Sigma Matters, and really here in the U.S. we have to wonder, under the Affordable Care Act, can we afford quality? Is it affordable care or is it assured care? Are we going to have quality? Then we're going to talk about Sigma metrics, Six Sigma as a way to benchmark the quality of our methods, and then we're going to go through some case studies and look at different instruments and how they measure up on the Sigma scale. We'll start with one tool here called the Sigma metric equation, which is simply how do you calculate the analytical Sigma metric of your method, what is the quality of your method. The second tool we'll use is the method decision chart, which is a visual tool. It allows you to just with a glance figure out, do I have good performance or poor performance? And then finally the OpSpecs chart, which is a design tool, a tool that allows you to redesign how you do QC so you can take advantage of high quality and perhaps widen your limits and loosen up your rules. And it also will allow you to figure out how to compensate for poor quality, how to apply more rules or different combinations of Westgard rules so that you can still guarantee the quality of the result, even if the method performance is not quite as good. So here is just a summary of what the last 2 years have been like for the Affordable Care Act. In 2014, we had them tell us we're going to cut off another $2.4 billion out of laboratory reimbursement. This is in addition to a cut of 20% over 20 years. And then they also had added this saying, for your highest volume tests, between 2017 and 2019, they have the right to cut your reimbursement rate by 10% each year. Then from 2020 to 2022, they have the right to cut your highest reimbursement or your highest volume tests from 15% every year. In other words, a grand total of more than a 50% cut to all your highest volume tests. Put more simply, the dollar that you're getting today is going to be 47 cents in 7 years. how is your lab going to deal with that? Have you tried telling your techs that their salary is going to go from $1 to 47 cents? Do you think your manufacturers, your vendors, are going to suddenly deeply discount the products that they're offering to you? We have to figure a way out of this particular economic problem. And it's not going to be allowed for us to raise our prices. Instead, we have to look internally. We have to look internally and figure out how is there waste? Is there waste we can work on and remove from our system? And that way, we can get rid of that waste and continue to exist. Now, this year, we had another regulation come down from CMS where we talked about a pivot from paying for volume to paying for value. So Medicare's traditional fee-for-service is going to go away. We're going to move towards bundled payments. We're going to move towards where they're no longer paying you for the amount of services you're doing, but for the value of it. They're not going to pay you on quantity. They're going to pay for you on quality. And by next year, they want 30% of that reimbursement tied to quality and value, 50% by 2018. If you're taking part in the value-based purchasing and the hospital readmission reduction program, then they want an even higher bar. They want 85% of your payments tied to quality and value, 90% by 2018. Now, what does that quality and value really mean? For many of those conditions, it's going to come down to where are the patients in relationship to their laboratory tests. They're going to ask you about your diabetics. We're going to now change how you reimburse clinicians on those HbA1c values. If you can't keep enough of those patients below a certain percentage HbA1c, the doctors get less money. That, of course, assumes your HbA1c results are accurate. If you've got a biased method, you're going to change the reimbursement of all your clinicians. So your laboratory test results are going to become ever more important to your clinicians. It's now not only about the patient, it's about all the money that's going to be tied to that patient's care. And the quality of your results will help determine how the whole healthcare system gets reimbursed. Now, again, part of this assumption is that all the manufacturers have the same level of quality. But more recently, we've seen studies that are telling us this is just not true. We cannot assume that the manufacturers are all the same. They're all giving us the same level of quality. And when we talk about what Dr. Litten and Dr. Bach have done to move beyond just achieving Six Sigma, we actually need to back up and say, are we sure we can hit Six Sigma first? And that means taking a look across all the vendors and assessing what's the quality they're achieving. So this is a study from the AACB, it's the Australian Association of Clinical Biochemists, looking at all the different manufacturers and looking at 27 different chemistry tests. And their goal is to try and establish a single reference range. A single reference range that any person walking in at any clinic, at any lab, with any instrument, having one reference interval for the entire country. Again, that assumes there are not big differences between manufacturers. So in order to prove or test that thesis, they decided we're going to send out a bunch of commutable patient samples, and we're going to test them all on these different manufacturers. And I realize this is quite a table. What you want to see is there are numbers in green and numbers in red, and each number in red is telling you when a manufacturer has gotten the highest amount of bias in class. And when a manufacturer has achieved a number, and we've highlighted it in green, that's the lowest amount of bias in class. So we can look through these 27 different chemistry tests. Here's the rest of those 27 chemistry tests, and then we can just add up how many times did a manufacturer achieve best-in-class performance, that is the lowest amount of bias in class for each analyte, and how many times did a manufacturer have the worst amount of bias? You would hope that that number ends up all being around the same number, that there's not that much difference between manufacturers. The result is actually quite different. We have DXC. There's one analyte out of 27 where it has the lowest amount of bias. Roche Modular 2, Olympus 3, Integra 3, Advia 4, Vitros 4, Dimension 6, and Architect 8 times has the leading lowest amount of bias in class for 27 chemistry tests. Now, on the other end of the scale, we would like to see that many manufacturers have as few times the most amount of bias per analyte. So here we have DXC having 7 times, it's got the highest amount of bias. Vitros 6, Dimension 4, Olympus 4, Modular 3, Integra, Advia, and then Architect 1. There's a big difference among the manufacturers. For some, this is something that they can overcome. For others, they might say, if we have this level of difference among manufacturers, we can't have a single reference range. The biases between some of these analytes, between these manufacturers, sometimes is 35% more than twice the amount of allowable error. So once we realize that we have to make sure these manufacturers are providing us a high-quality product, in order to verify that that's going to happen, we need to use a scale to measure the quality of the manufacturers. That's where Six Sigma is going to come in. It's our benchmarking tool. The concept is probably very familiar to you. We're trying to figure out how many times out of 1 million chances a process generates a defect. If you run 1 million tests, how many of those tests are defective? We put that on a scale of 0 to 6, where Six Sigma really denotes only 3.4 defects per 1 million tests. And in business and manufacturing, this is considered world-class quality. This is where an industry in manufacturing, if you achieve Six Sigma, you have your most reliable result, you have your most satisfied customer, they have the most amount of confidence in what you're delivering to them, you're also making your most profit. In contrast, if you're at something closer to 67,000 defects per million, 67,000 defects per million test results, that's called 3 Sigma. And 3 Sigma is the floor, according to manufacturing and industry. When you go below 3 Sigma, your process becomes too unstable. You're going to spend too much time doing that process over and over again. It's going to take you multiple times the effort to get one single good output of that process. When we see processes below 3 Sigma in healthcare, we see a lot of rework as well. We see a lot of repeated controls, recalibrations, more troubleshooting episodes, more need to go back and resample the patient. And when we see processes far below 3 Sigma, this might indicate the test is not fit for purpose. It might even be an indicator that the manufacturer will ultimately recall this method. Now, we've had a recent paper from the IFCC Committee on HbA1c standardization talking about the sigmametric model and looking at all the different models out there that are available and strongly recommending that sigmametrics is the model that is most flexible, and it's the model of choice when you're going to be looking at the quality of different methods. Now, they obviously were looking at HbA1c. They were only making their recommendation on a single test. But since this is a test that's been highly standardized and we've generated decades of effort to make that test better, I think it's telling that the IFCC has decided that sigmametrics and that model is really the way you should be looking at tests when you evaluate them. So we start with that Six Sigma as our model of choice, as our way of assessing quality. We need to get more specific. We need to say, for a specific test, what is the quality requirement for that test, that individual test? The quality requirement for HbA1c is going to be different than it is for troponin, than it is for cholesterol, than it is for glucose. You don't need to specify each individual quality requirement yourself. You can look it up. So if you belong to an EQA group or a proficiency testing group, or if here in the US, CLIA outright regulates more than 82 different analytes, In Australia and Asia, the Royal College of Pathologists. In Germany, the Phillip Bach rules. And then a very popular source of goals is called the RICOS goals. It's a biologic variation database, and for more than 350 different tests, it sets specifications for desirable, allowable total error. So these different goals, which you can look up all in a free section on the Westgard website, don't even have to be a member, but you can look up these goals. They tell you how big the target is. They tell you what is your error budget, and now you have to figure out, do you hit that target? Do you consume all the error budget? Or do you stay within your budget and still provide a high-quality test? In order to know whether or not you're hitting that target, that's where we need to measure our imprecision and our bias. This is where we take advantage of data you're already collecting. You're not going to be required to do an additional study or collect more data. You just have to look at the data you already have. Do you know the imprecision of your methods? Of course you do. You're running controls already. Do you know the bias of your methods? Well, there's a couple different ways you can calculate bias. One of them could be through something like the CAP survey, Proficiency Testing Survey, and EQA program. Periodically throughout the year, you get specimens, you figure out what your values are, and then you eventually compare them to what that EQA or PT program says this is the value you should have achieved or that your peer group is achieving. You could also belong to an actual peer group. So a bunch of similar instruments and similar reagent. You're comparing yourself against a peer group mean. You can do that very frequently and figure out, well, if my peer group mean is here and I'm all the way down there, that difference is a bias. And finally, one other way you could calculate bias is to use assay controls. If you don't have a PT survey to look at, or if you don't belong to a peer group, you might have controls that have target values assigned to them. And then you run that control and you figure out what your value is, compare it against the target assigned value. Again, that difference can be turned into a bias. So we've assembled three different numbers that are going to give us our sigma metric. First of all will be the quality requirement, which tells us our allowable total error, how big our target is. Then we need our imprecision, or CV, and then our bias, or inaccuracy. We put those three together, we have the sigma metric equation. So our sigma metric equation is total allowable error minus the bias divided by the CV. So your quality requirement minus your inaccuracy divided by your imprecision. And then the graphic here is just to give you a visual logic of how the equation works. When you exceed the allowable total error from where you should be, that's when you start generating false positives or false negatives. That bias is telling you you're not actually centered on the true value of the patient. The CV is telling you the spread of the distribution of your test results. So when you know that shift and that spread, you know where the curve is going to go, you know at which point it will exceed the allowable total error, and everything after that will be defects. The second tool is the method decision chart. This time we use our imprecision and our bias as XY coordinates. Your X coordinate is your imprecision, your bias is your Y coordinate. These different zones here are the sigma zones. 6 sigma is world class, excellent for 5, 4 for good, 3 for marginal, 2 for poor, less than 2 unacceptable. It's like a bullseye. Closer you get to that bullseye, the fewer defects you have, the more confidence you have in that test result. As bias increases, as imprecision increases, you are generating more defects. You are adding more noise to the test result, and you are adding more uncertainty into how the clinician is going to make their decision. And if you're all the way out here, you are probably confusing the clinician rather than helping to confirm any diagnosis. Now here's just a random analyzer. I will say this manufacturer is exhibiting on the floor. It's a new analyzer, so we have data from 2013. And let's say this is going to be your low bid. Okay, they're going to come in and promise you cheap. They're going to promise you fast. Do you think they're also going to have quality? They're going to tell you, oh yeah, we've got high quality. Do you want to make sure that's true? If you do, you want to see the CV, you want to see the bias, you want to look up the total allowable error and set those targets, and then you want to do a method decision chart and do some sigma metrics. And here you can see, well, there's about 3 out of 26 tests that are in the bullseye. but more than 50% of the levels being measured by this assay, by this analyzer, are below 3 sigma. And some of these up here, if I are tucked on the top of the graph, if I let them go, they will escape the international dungeon, and they will be on, I don't know, is it the marquee level is above us? That's where they are. Their bias is huge, and that has a clinical consequence. That means if somebody comes in from another facility and they get tested on this device, they could have wildly different results, and a clinician could make a decision that they shouldn't make. They might decide, oh my goodness, your numbers changed, I'm going to treat you, I'm going to diagnose you, I'm going to tell you you've got something. When in fact, that's just the difference caused by the noise of the system. George, I'm not going to say that. You think you might know who this is? Maybe. In contrast, here is the C4000, the Architect's the low volume instrument for chemistry. This is from the Kern Valley Hospital District. The laboratory director, Adam Summers, was kind enough to share this data with me. This is from 2015. And he's got 25 methods, and 23 of them are at 5 sigma and better. So in contrast to that other M-based analyzer, he's got very reliable results. He does not expect many defects in his test results. In fact, 92% are above 5 sigma. Now that's nice, but of course we really want to turn that S in 6 sigma into a dollar sign. That's what our administration is looking for. Money. Quality is great, but can we make that high quality into something that's going to impact bottom line? Well, we can by making it reduce our internal failures. Cut your expenses and controls, calibrators, reagents, reduce the number of false rejections being generated by your QC, and reduce the amount of time and effort that you're spending working that instrument. The other thing you can do is reduce the number of external failures. Fewer defects going out the door, that means fewer problems with diagnosis, fewer missed therapies, better patient care. And then even in maybe a more optimistic sense, when you see a bad test result causes confusion but not a misdiagnosis, it still causes a delay because the clinician looks at that number, realizes it doesn't make sense, and they say, let's test you again. Let's keep you in the system one day more. Let's run you through one more time. All of that is more expensive than we can afford. And particularly in light of the Affordable Care Act, you're not going to be able to absorb that kind of waste anymore. You've got to cut it out or you're not going to survive the new reimbursements. And then one final question, if we do take advantage of this high quality and we figure out, yes, we've got a high quality 6 sigma method, we can reduce our QC frequency, we can loosen our rules, we don't need Westgard rules maybe. How do we still feel confident that we've got quality assurance? That's where Dr. Bach will come in and talk about this average of normals and moving averages as a way to bridge the events of QC that tell you you're in control. The moving average tells you in real time, hey, everything is still good with our patients. All right? Our final tool is the OpSpecs chart. Again, imprecision is on our x-axis, bias is on our y-axis. We're plotting our CV and bias as XY coordinates. Now we've got different lines that represent QC procedures. It's still just like a bullseye. If you're within a certain ring of a target, that line, let's say, will correspond with the QC procedure that you can use that gives you enough error detection that provides you the right quality assurance. But if you are outside one of those rings of the target, you're outside one of those lines, that tells you that QC procedure isn't good enough. You can't use it. It's not going to give you the error detection you need. It's not going to provide you the quality assurance for that test. The closer you get to the bullseye with an OpSpecs chart, that means you're going to have wider limits. And you could have fewer controls, and you will not need Westgard rules. But as you have more imprecision, as you have more bias, you will need more controls, you will need Westgard rules, you will need tighter limits, and out here, QC isn't going to save you. You run all the Westgard rules you can afford, run multiple controls, By the time you detect that error, it's already out the door. Previous runs have probably already been impacted. Patient care has already been impacted. So here we are with our anonymous analyzer. How do we do QC for this particular device? A couple of these analytes are in the bullseye. We could go to 3S rule, 3S limits, 2 controls, no Westgard rules needed. All of these analytes here, they need all the Westgard rules, maybe double or triple the number of controls you're used to. Out here, again, up on the marquee level, our assay performance, we really possibly should consider only running QC. Because if we only run QC, it will prevent us from running patients. We will not have the danger of erroneous patient results. In contrast, if we have, here's the C4000, about 22 out of 25 of those assays can be controlled easily with 3S limits, 2 controls. The glucose and the CO2 need a mini Westgard rule combination of 3S, 2S, and the magnesium and the calcium are the problem children. They are going to need a Westgard rule set here. Just 4 of the Westgard rules, 2 controls, looking back 1 run. Still only a small false rejection rate of 2%. All of that, as Joe Litten will show you, can result in hard dollar and soft dollar savings. So here's Joe. I'm sorry, I'm going to steal a little bit of the thunder of our next speakers. I'm going to tell you that they are able to achieve high levels of quality so that then when they come up, they're going to tell you what they did next, what they did after that, how did they go beyond just achieving high quality. So here's his 2 C8000, so that's the mid-volume chemistry architects. And again, about 90% of his analytes are close enough to the bullseye that he can use 3S limits and no Westgard rules. His problem children are urea, sodium, and CO2. Those are the ones that he's got to use some Westgard rules and keep an eye on. And then when we look at Dr. Bach has 3 C16000s. So he's got a very high-volume laboratory. He's got the high-volume chemistry systems. And again, a majority of his analytes are very close to the bullseye. He has very little to worry about. A couple analytes, maybe the potassium, the phosphate, chloride. There's a couple things that will be very well monitored if he can use the additional power of moving averages. All right, so to conclude and really to hand off to the next speakers, again, Six Sigma is a nice achievement, but it really is only a start. Because while it's nice to make sure we've got easier operation, that we've saved money, what's more important is that we're still assuring the quality for patients and clinicians. That's what Dr. Litten and Dr. Bach will be showing us. And I'm just going to quickly recap. We had 3 different tools, the supermetric equation, method decision chart, OpSpecs chart. All of those are available at the Westgard website in free downloadable forms. So these tools are available to you now in a way that you can start working on this as soon as you want. And with that, I'll thank you. Sorry, I'm going this way. Thank you very much for your attention. I want you to hold some if you have questions, please hold them till the end of the talk when we've got all 3 speakers up here. And thank you very much for your attention.
Thank you very much, Sten. Our next speaker will be Dr. Joe Litten, who is the Corporate Technical and Development Manager at Valley Health System in Winchester, Virginia. He received his PhD from the Medical College of Virginia and later accepted a position at Western Maryland Health System in Cumberland, Maryland, where he was responsible for the chemistry department and point-of-care testing, and where in 2004 he helped to install their Beckman-Coulter chemistry automation line. In 2006, Dr. Litten became the technical director for Piedmont Medical Laboratory in Winchester. In 2008, Piedmont Medical Laboratory became the first laboratory in the U.S. to receive ISO 15189 accreditation from the College of American Pathologists. In 2010, he became the technical and development manager at the Valley Health System. He implemented a complete Abbott automation line in 2011 and is currently overseeing standardization of chemistry and immunoassays throughout the system. Additionally, he is implementing a stringent QC program at the main hospital to include Bio-Rad Unity real-time, moving averages, Westgard analysis, and Six Sigma analysis. Future plans include standardization of the hospital program throughout the system and implementing a peer review program within the system. He also looks to enhance efficiencies with auto-verification through a middleware solution for the entire system. And Dr. Litten has been a member of the AACC since 1975. The title of Dr. Litten's presentation is Applications of Six Sigma Metrics. Please welcome Dr. Litten to the stage.
Thank you, Alex. I appreciate that. It's always hard to follow Sten. He has a lot of good stories. He lived by the Westgard rules. I grew up by the Litten rules. So I think they probably were somewhat the same. Winchester Valley, well, before I start, just disclosure of my time. I have been reimbursed by Abbott for my time here. Winchester, Virginia, for people who don't know, is about 60 miles due west of Washington, D.C. And it's at the north end of the Shenandoah Valley, and you can see the picture there, the Blue Ridge Mountains, just to the south of Winchester. It's a 6-hospital system. The main flagship hospital is Winchester, and then there are 5 smaller feeder-type hospitals in local communities as far south as Luray, Virginia, and over in the West Virginia at Berkeley Springs and Romney. But most of the beds, of the 600 licensed beds, most of those beds are at Winchester. I think it's a little bit over 400 beds hospital. One of the things we wanted to do, one of our goals was to standardize throughout the healthcare system. So what we have at the 6 hospitals, we all have the same chemistry instrumentation. The smaller hospitals have C4000s and I1000s. Winchester has C8000s and I2000s. And we do around 3.5 million tests a year. Again, most of those are performed at the Winchester facility. Back about 5 years ago, we were in the boat. We were looking for new instrumentation. Again, we wanted to standardize. It was important for the health system to do that because, again, the feeder hospitals are referring patients into Winchester Medical Center. So we wanted to make sure we all had the same reference ranges and pretty much the same results. But we made a list, and this was just a partial of the list. But I think most of these things that are on the list here are probably on everyone's list when you go looking for new instrumentation. Reliability was big for us. It was probably the top of the list because the instrumentation we had at the time, we were really having a lot of reliability problems. The techs always want to know about the ease of use, the cost. Of course, my good friend, the CEO, Mr. Lewis, was very interested in our cost. Specimen requirements of phlebotomists want to know, like all the tests to be done on one type of specimen. The turnaround times, of course, the ED wants, and your units want good turnaround times. Testing menu, of course, that improves your process internally in the lab if you have fewer boxes. And of course, the throughput's important, especially in morning draws or when the volumes are extremely high. And vendor support was another big issue for us because, again, we were having major problems with the vendor. We were having problems with reliability instruments, and also we were having issues with our vendor support. But one thing I wanted to throw into this, I had read, of course, I guess it's been about 12 years ago, so at least, Dr. Westgard's book on Six Sigma design quality control. And I thought, hey, this really makes sense. Can we implement this? Is there a way we can utilize this? So I wanted to see, and when we started this, we wanted to see, could we compare the quality results that we would get from one vendor to another? And I thought the easiest way to do that was through Six Sigma. It's kind of a way of comparing apples to apples. And the reason we wanted to go that route is if we could have a system that gave us high quality results, high analytical accuracy and good precision, that we could use simpler Westgard rules or QC rules, and we could also use fewer challenges to monitor those tests. And that's going to result in less cost and less labor. So it was something, it was kind of, could we do it or not? It was kind of an experiment. So what we did was we used, for total allowable error, we used the CLIA regs, because we are here in the United States. For some of the tests, such as phosphorus, we used CAP limits that they had developed. And we looked at 30 different chemistries. And we used data from the 2009-2010 CAP surveys to give us an indication of the precision of each vendor. And we looked at it from standpoints of, like for glucose, what we're really interested in was glucose specimens that had the levels around 100 to 130, because we felt that was a very critical area for glucose. And we did the same thing for all the other tests. So it was kind of around method, clinical decision limits. So when we did this, what we thought we could do is maybe separate out the top 2 or 3 vendors or instruments from the lower performers. In green, what we looked for was a 5 and 6 sigma test. It was 5 and 6 sigma tests. We knew from Dr. Westgard's book on 6 sigma design that we could use very simple Westgard rules such as a 1.3S or even a 1.3.5S and a challenge of two levels of QC a run. So that was something we thought if we could come up with a vendor that had a lot of those 5, 6 sigma tests, we could redesign our QC program and really get the max out of it, where we would have less labor and less expense. So when you look at this, we were surprised to see that Abbott stood out. You can see they have a lot of green here in the graph to the right compared to the other vendors. The yellow or the kind of off yellow, orange, those were 3 and 4 sigma tests. So we could live with that. I mean, you just have to use more Westgard rules to monitor your tests. You may have to run a few extra controls per run, but something you could control. But the red would be anything under 3 sigma. If you looked at the chart that Sten had put up, you really, once you go below 3 sigma, you really have a tough time really adequately monitoring that test. You have to run a lot of challenges, maybe 6 or 8 challenges per run, plus you have to use 6, 8 different Westgard rules to really adequately monitor the performance of that test. So we didn't want any red, and what we found was, interestingly, was that all the other vendors, we looked at 6 of them, and actually I think all 6 of them are still on the floor today at the convention center. We found that one vendor had 1, but the others had at least 3 or 4 tests that were below 3 sigma. So that was kind of eye-opening to us because we knew with those tests we'd have a problem adequately monitoring those tests, the performance of those tests. So, long story short, we went with Abbott. It was partly this, partly other things, issues that we had that we liked Abbott's system better than the other vendors. And that data, the data I'm presenting here was from 2011 when we brought the instruments in. And the chart here is what we estimated we would have. Here, though, the green is 6, the yellow is 5 sigma, this is 4, and this is 3. And that's what we estimated. We estimated we would have nothing under 3. What we found was about 77% of the tests were 6 sigma or better. Now, we expected to be better performance because usually, if your lab compares to a group of lab, you're going to get better CVs and your bias is going to be more in your control. So we expected a better performance, but we didn't expect this much of a better performance, 77%. Another 17% was 5 sigma. And then we had 2 tests. Well, actually, it's 3. One was uric acid, but we corrected that by going to the new uric acid. I'll get into that in a minute. But we had 1.4 and 1.3. And what the good thing about all this is I had nothing below 3. So the two, we had the sodium, which on average runs in the 4 sigma. And I'll go into that a little more. We can get it at the 5 sigma level. We just have to do maintenance and preventive maintenance to keep it up there. And the other one was CO2, which we figured we'd have a problem with. So this is our original data from 2011. You'll see here the rules. What we did was we incorporated the Biorad Unity real-time program. And the first year, I bought the Westgard Advisor, which comes with that program. So the Westgard Advisor looks at peer data from other laboratories, Abbott laboratories that are using our equipment and using our QC, using the same lot number QC. So we did have the bias compared to other Abbott laboratories. And they also take our CVs and they calculate the sigma metric for us. And they tell us what rules we could use to get away, what rules we would need to monitor the test. And you can see there's some tests we could do with a 5S or a 4S. I can say we don't use that. I get a little upset when I look at the CVs or the Levi's-Jennings charts and I see things above 2 SDs. So my techs didn't like to see things above 3 or 4 SDs, so we never went to those rules, but I guess we could have if we wanted to. But if you look, this is the Chem 8, and looking at this, you can see some great CVs. All the CVs were under 2% except for the CO2. And I think a couple of the ones that stand out is the chloride at 0.7%. Glucose was less than 1%. It was really, we were amazed at the CVs we were seeing from this instrument. And this is some more of the tests, and the one I have highlighted here is cholesterol, because that was one we were very interested in. And you'll notice that at a control of 100, our CVs are around 0.9%. At 200, the control of 200, they're less than 1%. So, this is something we just, I've never seen with any other instrumentation I've had in the clinical lab, and I think I've used just about every instrument out there one time or another. And this is a chart that Sten did for us. You'll see the uric acid here, and if you go back, you'll see the original uric acid. We had sigma 3. In 2012, we went to the new uric acid, and you can see our CVs went from just under 5% down to about a little over 1.5%. So it went from a 3 sigma to well over a 6 sigma. So the good thing about this is everything is to the left, lower left. That's where you want to be. This next 2 slides I'm going to show is just a Chem 8, and this is taken from one of our analyzers from Maze QC data. And you can see the sodiums we generally run anywhere from, in this month we were in the mid-3s to the mid-4s. If I go in, we found 2 things with the sodiums. If we keep the syringes, preventive maintenance on syringes every 2 months or so, and rebuild the syringes, and also keep an eye on our cal factors, we can actually keep the sodium sigmas to 5 sigma or better. And we see this not only with the C8000, but I also see it with the C4000s at the other facilities. The chlorides, you can see, again, we're allowed 5%. So all of these chlorides are giving us sigma metrics of 6-7%, which really is amazing. And the CO2s, again, they're probably the problem child that we have with the instrument. Calcium, you can see the sigma metrics are 8, 5, and 6. Now, this is based off. We don't use the CLIA-defined allowable level there of 1.0. If I were to tell our physicians that your calcium on the patient is 9 plus or minus 1, they probably wouldn't like that. So we use 0.5. And even at 0.5, you can see that our sigma metrics still over 5 to 6. Creatinines, very low CVs, the BUNs. I know the data that Sten showed on the BUNs, we were having some issues. What I do is every quarter I do a quarterly calculation, and I send that off to Sten. And the month I think that he had, we were having some issues with the BUNs, but you can see they've settled down well in May, that we were getting the CVs back to where we expect them to be. Glucose, you can see from 58 up to 300, the CVs were 1% or less. So what does that mean? Well, that means we go back to really what Sten was talking about, the Six Sigma designed quality control program. And the thing with that is that if you can have a vendor that has a lot of high sigma tests, you really can take advantage of a QC program like this. And what you're looking for is when you come up with that program is you want something that's going to detect 90% of the clinically significant error and also at the same time give you a very low false rejection rate. So when you do have an outlier, you know that you have a clinically significant error, and at the same time, you figure it's probably not a false rejection. So there's probably a very good likelihood you do have an issue with that test. So what we were able to do was, if you look at our program that we started with our previous vendor, we were running 7 QC challenges a day, and believe me, for some of the tests, we needed that probably more. We were doing 3 levels of QC on day shift, 2 in the evening, and 2 at night. What we were able to do with this instrument, we've gone to a 12-hour running QC every 12 hours, and we run 2 levels. And by doing that, we can do this because of the high quality. 27, 28 of the 30 tests are 5 sigma or better. And by doing this, if you can come up with this program, what you see is you have fewer false warnings and or rejections. What happens is with technologists is if they see a lot of rejections, QC failures, they get kind of immune to them, and they just kind of run them, and they really don't take a look at what's going on because they figure that it's probably just a false rejection. So what we were able to do is by going to the Six Sigma quality design is we have fewer false warnings, there's less tech time, and I think Sten pointed this out, to investigate the failures, which means looking at the instrument, what's going on with the reagents. There's less tech time involved in running QC and reviewing the QC. There's fewer repeats of QC material, and we also found there's far fewer calibrations. Now, when we did this, before we went to the Six Sigma design program, I ran it in background for 3 months. So we had our traditional way of doing it, and then we had the Six Sigma design. So we knew from that data that all these things were going to happen. The time savings was going to be very significant. And what we found was, by changing our QC program, we found that we saved 45% savings for both the Chem8s. We also do the Sigmametrics for our IAs. And just on the cardiac side, we were able to save $55,000 a year in reagents. These things, it was surprising to me. I knew we were overrunning QC, but you don't realize how much money you're wasting until you actually sit down and start looking total and up. Control materials even, we were going to save, calculate we'd save at least $10,000 a year. And labor savings, and believe me, this is conservative, 50% savings in labor. Instead of probably spending anywhere from 3 to 4 hours or more a day running QC and doing the repeats and everything, we're down to probably a little over an hour a day, and there's very few outliers. So we wanted to, so I was curious, how many outliers do we have? What's our failure rate? And I wanted to look at the failure rate by the sigma metric of the test. So we looked at 70 different tests on our Chem8s, our C8000s, and our I2000s. And we had, over a 3-month period, we had over 45 QC points that we looked at. And at any time, in any day, we would run anywhere from 2 to 4 QC challenges. Urines, we run 2 a day. We don't do a lot of urine chemistries, so we feel like 2 QC runs a day, checks a day, is more than adequate. And believe me, we have very few failures of QC for our urines chemistries. The rules that we use to monitor our tests, if it's a Six Sigma, we use a 3.5. We can get away with that because the Bio-Rad Unity program allows us to institute this rule. A lot of LISs, you're not able to use a 3.5 rule. They just don't have that rule. The 5 Sigma, we use a 3S, and then the 3 and 4 Sigma, we use a multi-Westgard rules to monitor their test. So what we found was that the failure rates for QC for the 3 and the 4 Sigma test was over 20 times higher than the 6 Sigma test, and 7 times higher than the 5 Sigma. So if you look at the rates, for 6 Sigma, you're at 0.7, the 5 Sigma, you're at 2.1. And that's important. If you have a system that you can have, high quality tests, 5, 6 Sigma, you can see your QC failure rate is going to be very low. You can see for the 3 and 4 Sigma test, we were at over 14% failures. We also looked at, for the 5 and the 6 Sigma tests, going back to looking at traditional QC, where a lot of people still use the 2SD to monitor, or at least just to check on their test. We found that for the 5 and the 6 Sigma methods, that the number of test results that we accepted, okay, because we could use a 3SD or 3.5 SD rule, we found that 6% of our control values were within that range, but they still were okay because it was not a clinically significant error. For the 6 Sigma test, we found that 0.5% of the test results were in the 3 to 3.5. Again, we allowed those to happen because, again, it's not a clinically significant error. Interestingly, I wanted to go back and look at the 5 and 6 Sigma. This is a work in progress. I'm trying to get my text to be a little more explicit about why there was an error. You can still see 50% of the time they're really not telling me what the issue was. But interestingly, a third of the failures for our 5 and 6 Sigma test is because they ran the wrong QC. They either picked up the wrong QC or they reversed it. Recalibration was about 12% of the time we need to recalibrate. Instrument issues, another 3%, and reagent issues were around 3%. So I'm working on them. They're getting better at documenting why, how they fixed the problem. As I mentioned earlier, when we started this whole process, we wanted to standardize. We wanted to standardize from our outlying hospitals to the main hospital in Winchester. And we knew patients would be transferred from the smaller hospitals into Winchester. Plus, we knew the outreach program. If we ran, all the outreach work is being run up at Winchester. But if they go into one of the smaller hospitals, the reference ranges are the same. And we wanted to show and make sure that our values we were getting were the same. So we came up with limits. This is how close we want our specimens to be. Albumin, 0.3 grams per deciliter. Some of these are internal. Some of these are Dr. Ricos's from her database. And some, like the BUN, is a CLIA. What we do every month is, and we do it toward the end of the month, is I prepare 5 pooled specimens, patient specimens. And from those patient specimens, I'll take some of our liver disease patients or our diabetic patients, patients that have heart attacks, and I pool them together. And through processes of cleaning them up, I've actually gotten fairly good of being able to give us everybody 5 specimens, and we all run them the same day. I send them out, we keep them refrigerated, and then on a Wednesday afternoon between 12 and 2, everybody runs them, and then sends me back the results. So we wanted to do that to see if we could keep a high-quality results, consistent results from each hospital. So what I'm going to show you is basically 9 different tests. We do 30. Actually, it's 29 because we've finally got permission to get rid of the CKMBs, and they will be going by the wayside here before the end of August. This is sodium. This was over a 10-month period, so it was 50 specimens from 6 hospitals. Actually, from 7 instruments, there was 5 of them were C4000s and 2 C8000s. And you can see our limits here is we want them to be within 3 units of each other. We had 1 failure that was at 4. Every other test from 120 up to 150 fell into that range. So we were happy with that. I'd like to get it down to 2, but so far we haven't been able to accomplish that. I think with these instruments, 3 is about the best we're going to get. Potassium, 5.6%, that's around 0.2, 0.3. I think that's Dr. Ricos's limits. And you can see from 4 to 6.5, over 50 specimens from the six hospitals, there were no outliers. Chlorides, 2.5%. That's somewhere between a 2 and a 3 milliequivalent per liter difference. Again, from 85 to 115, there were no outliers for the whole period. And I could throw in the first 6 months of this year. This data was from 2014. But if I throw in the first 6 months of this year, again, there was no failures. CO2s, we did have a failure. We used 2 and 12% from 15 to 20 up to 30. And we did have one time when we had a problem with one of the instruments. We found it to be a calibration issue, and that was corrected, and we haven't had any problems with that since. Calcium at 0.4. Again, from 7.5 up to 10, there was no outliers from any of the labs. Glucose at 6.9%, plus minus 4. Again, this is Dr. Ricos's levels. You can see from 100 to 500, there were no outliers. Creatinine, again, this is Dr. Ricos's range, 8.9%. Again, no outliers from any of the sites. So we're getting good, consistent results on a Chem 8. BUN, this is one, since I have issues, I have to keep an eye on the BUNs at all the sites as far as the daily QC goes. We used the 2, plus minus 2 and 9%. This is one where I thought we were going to have some issues. But, from around 10 up to over 100, we've never had an outlier. And if I threw in the 6 months from this year, it would be the same thing. We've never had an outlier on BUNs, which I was pleasantly surprised at that. Cholesterol, I just wanted to throw cholesterol in here. It's 5%. From 50 up to almost 300, we had no outliers during that period of time. We want to get it down to 3%. That's where the NCEP recommendations is, plus or minus 3%. And you can see we had a couple outliers at 3%. We found this to be a calibration issues going on. Cholesterol is calibrated about once every 30 days on these instruments. So we went to the sites and had them recalibrate. I think it happened twice. That problem, it corrected the problem. Looked at the first 6 months of this year at 3%, so that's what we're using now is 3%. We've had one outlier out of the 25 specimens from the 6 different labs, and that was just under 4% off. So it was more than 3%, but it was less than 4%. So we are able to get good, consistent results, and that was important. That was one of the big things we wanted when we looked at the instrumentation. So in summary, what I can say is that you can use sigma metrics to help compare when you're looking at instrumentation one instrument to another. It does give you a good apples-to-apples comparison. And will also help you determine can you institute and get the full advantage of a Six Sigma design QC program. Also, the Abbott's, over 90% of the Abbott tests are high quality on the chemistry instrument. We were able to change our QC program, which resulted in significant savings in materials and labor. And the 5 and 6 Sigma chemistry methods, we had far failures than the 4 Sigma or below test, which is important. And there's excellent correlation that we get from our different hospital labs. Okay, so thank you.
You guys are almost there. One more presentation to go today. So thank you for your patience. I know we started late. If you give our final speaker, Dr. Bach, your undivided attention, we promise we'll open up the bar. So hang in there for one more presentation. He's got a very interesting set of data. So Dr. Bach is a clinical chemist for Intermountain Healthcare and adjunct assistant professor of pathology at the University of Utah Medical Center in Salt Lake City. He received his PhD in biochemistry from Oregon Health Sciences University and completed a postdoctoral fellowship in clinical chemistry at Louisiana State University Medical Center in New Orleans. He has been a member of AACC since 1977 and is certified by the American Board of Clinical Chemistry. Before joining Intermountain Healthcare in 1987, he was a clinical chemist for the Clinical Laboratory Medical Group, a part of the Bioscience Laboratories, and worked for 2 years as a developmental chemist at Beckman Coulter in Brea, California. His current responsibilities include technical supervision of the laboratories at Primary Children's Hospital in Salt Lake City and Intermountain Health Central Laboratory in Murray, Utah, and direction of point-of-care testing aboard aircraft for Intermountain Life flights. The automated laboratory in Murray, Utah was the first Abbott automated lab in North America back in 2006 and is currently one of the largest in North America. He also shares technical oversight of 23 other Intermountain Healthcare laboratories in Utah and Idaho. The title of Dr. Bach's presentation is Patient-Focused Quality Control. Please welcome Dr. Bach to the stage.
Okay, am I live? I think it's working. Okay, great. First of all, thank you to Sten and to Joe for some very interesting material. I must admit I haven't gotten into that as far as I should. And so I'm motivated to get into this when we get back home from Atlanta. But tonight I want to turn a little page a bit and talk about what has been called patient-focused QC, using something other than control material to monitor the performance of tests. While I'm at it, I'm going to show you a few pictures I've taken from different national parks in and around the state of Utah, just for fun. So, okay, with that, let's go. Before I show data, I need to give you a little perspective on what is Intermountain Healthcare, what is Intermountain Central Lab, so you'll have a framework to hang some of this on. Intermountain Healthcare is a 22-hospital system in Utah and one up in southern Idaho, as you can see on the map there. These are the hospitals. They range from 500-bed tertiary care, level 1 trauma center, Intermountain Medical Center in Salt Lake City, to half a dozen small rural hospitals, 15 to 20 bed, in towns like this one, which happens to be in Panguitch, Utah, which is right next to Bryce Canyon. All told, we have 72 Abbott chemistry and immunochemistry, I should say modules, because most of these are married together as a CI system. The central lab is located at Intermountain Medical Center in Salt Lake. It serves basically 3 kinds of clients. First of all, it's the only lab for the hospital, and so it serves intensive care units in the emergency room and all that. It's also the first level reference lab for the other 21 hospitals in our system. And finally, we serve a large number of clinics and physicians' offices in the Salt Lake City metropolitan area. So you can see with that kind of a mix of customers and clients, you need to provide both fast turnaround time and high throughput. In the last 12 months, we ran just under 7 million chemistry and immunochemistry tests. As Alex mentioned, this was Abbott's first track in the U.S., and I think it's still the longest one. We currently have 3 C16000s, a C8000, and 4 I2000 SRs, as well as some other instruments that are not on the track, because right now with our track hardware, the limit is 8 instruments. Okay, for information systems, we have a Sunquest LIS, we have Data Innovations Instrument Manager, which runs the track, and we have something we like to call our EDW, or Enterprise Data Warehouse. That's what the figure is about. It's just an enormous Oracle database that takes information from all over our healthcare system, including lab information, stores it in this gigantic file server system somewhere, and can be queried with remarkable speed. Among other things, it has every lab result that Intermountain Healthcare has generated since 2006, not just the 2 labs I talked about, but all 22 hospitals. Okay, what is patient-focused QC? It's a term that was coined, I think, about 20 years ago, maybe even longer than this, by George Klee at Mayo Clinic. Basically, patient-focused QC is using patient data to monitor the performance of lab tests. I want to tell you about 2 ways we're doing this. We're doing more than 2, but time doesn't permit. We're using moving averages, which is nothing new to those of you who have been doing hematology, but it's now becoming available from many LIS and middleware vendors. We happen to be using the package on Data Innovations Instrument Manager for moving averages. We're also using that EDW data warehouse I mentioned to generate weekly median data from the lab database for a selected number of tests, not every one, but several. We're also using it to do other kinds of patient-focused QC I won't have a chance to talk about, such as plotting the percentage positive screens for hepatitis or HIV tests. Well, if that's what patient-focused QC is, why do it? Well, the first reason is that, as everyone knows, you don't run controls continuously, you run them periodically. And it would be nice to monitor your tests' performance continuously. So one reason is that controls are run periodically. For various reasons, controls don't catch every problem. Of course, nothing catches every problem, but we have an independent referee in addition to QC when we're doing patient-focused QC. Some of the reasons controls don't catch every problem, and I'm sure you're familiar with all of these. Controls are not necessarily fresh human serum. Controls can go bad. You can have an incorrect target range for a control. In some cases, the CV of the test is so large that the control range needs to be pretty wide. You'll have many, many, many false alarms. And of course, once in a while, controls just aren't run when they should be. I think, though, my most heartfelt reason for doing patient-focused QC is that patients are the bottom line. The buck stops there. If patient results have changed, if clinicians are complaining about a test, even if the QC looks okay, I have a problem. Okay, let's get a little practical here. Some practical considerations for moving averages. What is a moving average? Is basically the average of the current result plus the previous n results. You get to choose the n. And the same, of course, for a moving median. It's be the median of this result plus the previous n results. How do you set up moving averages? You need to do 3 things. You need to choose which tests you're going to use it with. You need to define the algorithm. And at least in the beginning, you need to expect to revise both of those frequently. At least I did. Okay, choosing tests wisely. A test that's suitable for moving averages or moving medians has three characteristics. First, it's run often enough that it will give you sufficient data for meaningful, timely alerts. Second, the results are at least usually within a reasonably narrow distribution range. And then finally, you're not going to waste your time doing this on tests that clinicians don't respond to when there's a fairly small change in the results. Okay, some examples. Sodium is a great candidate for moving averages. First of all, you run lots of sodiums. Most sodium results fall in a fairly narrow range between about 130 and 150 millimoles per liter. And clinicians respond quickly to changes in electrolytes. Okay, so sodium's a good candidate for moving averages. On the other hand, HCG is a lousy candidate for moving averages. Yes, we do run lots of HCGs, but most of them aren't detectable because most of them we run are on women of childbearing age before a procedure or a medication that might harm a fetus. The ones that are detectable can range from 1 to over 250,000, and so it's definitely not in a narrow range of results. And finally, clinicians know that if a patient's sodium changed from 130 to 150, everybody would notice, but if an HCG, those are essentially equivalent results. Okay. Having chosen your test, you need to define the algorithm. Okay. I like medians better than averages, and this chart illustrates why. Here are 9 consecutive serum creatinine results, right in the middle of which is a really high outlier. The median value for those 9 results is 0.75. The average, including the outlier, is 2.33. The average, if you remove the outlier, is 0.68, or essentially the same as the median. And so an extreme outlier can blow up a moving average. Nevertheless, you can use moving averages if you exclude outliers, define the range of results that you're going to let into the algorithm. If you do that, they work great. I understand that version 8.1.3 of Instrument Manager can actually do moving medians, so I look forward to getting onto that one. I'm currently on 8.1.2, which only does averages. Okay, having chosen that, the next thing you need to do is choose your N. Okay, and it's a balance, it's a trade-off between sensitivity to detect a small change and response time to detect an abrupt change that could create problems. So here are a couple of examples. These are screenshots right off of Instrument Manager, by the way. A large N gives you nice, smooth moving averages, but it responds slowly to changes. So we use this to detect slow drifts with clinical significance. There are 3 lines on there because I have 3 instruments running this particular test. On the other hand, a small N gives you a noisy moving averages plot. You can see that from this N of 25. On the other hand, it's quicker to detect sudden changes. And so you need to decide what N you're going to use for a given test based on what kind of things could go wrong with it and what clinical impact that could have. This is just a list of all the tests I'm using moving averages on right now. Obviously, the test name needs no explanation. Filter is the range of results that we permit into the algorithm. So, for example, for albumin, we let values between 3 and 5 into it. And N is, of course, the number of results that we average. You notice troponins in red. There's a software bug in version 8.12 of Instrument Manager that miscalculates moving averages if the instrument sends more than 2 decimal places. I understand that's been cured in 8.1.3, so again, I look forward to getting into 8.1.3. Okay, some examples of moving averages. This is a show and tell. I've been collecting these since Abbott asked me to do this talk 6 months ago. Here's one where an instrument needed maintenance. The instrument shown by the dark blue line there just was drifting downward in sodium until it hit the yellow line and sent me an email. QC at this point had not failed, but because of this alarm, we did some troubleshooting, found that the instrument needed something. I can't remember what it needed, but something needed to be replaced. And as soon as we did that, you can see that the moving average moved back up to the mean. It didn't jump back up because we're averaging 100 points, remember? So you have good results going in, but you have to wait for the low ones to bleed on out. Okay, here's an example. I mentioned earlier if your controls have a rather wide range because the test is got a high CV, you might not pick up a small change overall. This is vitamin B12, and those of you that run a B12 know that the CV of B12 is fairly high. So here's one where QC never said anything, but the moving average went up, hit not only the yellow warning line, but the red line, sent lots of emails. So again, we investigated. In this case, the instrument needed a new R2 reagent probe, so that was replaced. The test was recalibrated, and it came back down where it should be. Here's a rather striking example of a couple of outliers. This happens to be the HIV antigen antibody combo assay with an N of 25, and there were 2 patient results that were just below the top of the range of results we allow into the moving averages, and you can see how it just jumped up suddenly. This mouse is really sensitive. It just jumped up here, and then 25 results later, it jumped back down where it belonged again. Not a problem, just an illustration of what an outlier can do. Here's one. Patient populations. This is total calcium for 3 instruments over an approximately 24-hour period. Does anyone know why there's a valley in the middle of that plot for all 3 instruments? Okay. It's called morning draw. All right. Hospitalized patients have lower calciums, potassiums, albumins, and total proteins. And so each day in our moving averages plot, we see this valley for those tests. What's going on with PSA on instrument 4 with the purple line there? I got emails about this one and investigated, and there was nothing wrong. What happened was that just about 8 or 10 fairly high PSA patients in the range of 4 to 10, which is the highest value I led into the algorithm, just happened to hit that instrument in a short period of time and pushed up the moving average. But the take-home message here is you need to investigate patient-focused QC failures the same way you investigate out-of-range QC. It might be an instrument problem, but it might not. Okay, turning a page, I mentioned that we did weekly median values for all of our instruments based on our own database from the EDW. It's a query that runs once a week automatically and tabulates and plots median patient values for sodium, potassium, calcium, total protein, and urine albumin for all of the instruments in our system. Why those tests? Those are the ones that clinicians complain about when they go off. As for albumin, it was just to monitor a reagent carryover issue. So some examples of this. If I say moving averages now, it's because I didn't shift mental gears. I'm supposed to say medians now. Anyway, here's an example of a lot change, reagent lot change in calcium. This wasn't an Abbott instrument. It was just before we installed our C4000 at this place. But there was a lot change at that red arrow, and it took, well, it was quite a jump from 9.3 median to 8.7 median, which is a great big change for calciums. And the way we fixed this one was we just put a new analyzer in. That was just before we installed the CI4100 there. Anyway, but the medians went back where they belonged after that. Here's an example of a boo-boo. Okay, what happened, again, a non-Abbott instrument, they put in a different lot of electrolyte reference fluid and forgot to recalibrate the test. On this particular instrument, you only have to calibrate with lot changes or every 6 months. Okay, so a bad calibration or something like this can perpetuate for quite a while with this instrument. QC was high, but it was not out of range. Okay. Now, I have to be kind to the folks. I did not run this report until the day shown by the green arrow. And so people were not staring at a huge shift like this for 6 weeks and doing nothing with it. We were still working on the report, but when I ran it, I called the lab that this occurred at and said, say, would you check out your sodiums? They just jumped up about 6 weeks ago. And they came back and said, yes, we forgot to recalibrate when we changed the electrolyte reference fluid. So they recalibrated, and you can see that the medians went right back where they had been. Okay, our children's hospital has a head trauma protocol, and the clinicians will adjust the IV fluid if the sodium changes by more than 2 millimoles per liter. And as you know, that's a really tight range to be shooting for. With our old instruments, I was just recently asked this, with our old instruments, we always had to run the patient on the same instrument. And the reason for that was that the two instruments didn't always match each other within 2 millimoles per liter. Do we still have to do this? We got new instruments now. Do I still have to do that? Well, if you look at the median results for 12 weeks here, they're completely flat, and they're never more than 1 millimole per liter apart. And so based on this and based on QC, I said, no, we don't have to do this only on one instrument anymore. Has anyone ever gotten a phone call like this from, say, a physician's office? Your potassiums are getting higher and higher. Always makes you wonder if you have a problem with the test that you weren't aware of. But in this case, I brought up our plot again of medians. Please disregard the blue dots. Yes, they're the most obvious ones on there, but that happens to be the instrument that gets all the neonates and dilutions and cruddy specimens, so I wouldn't expect its median values to be the same as the other three. But the other three are, again, just as completely flat as they can be and superimposed on each other. And since they were that way, it was pretty clear that this particular clinic had a pre-analytical problem, perhaps a centrifuge that wasn't working, but it needed troubleshooting at the pre-analytical stage, not the analytical stage. Here's an example of calcium reagent on an instrument that was deteriorating and people weren't paying attention. The medians began drifting upward on March 29th, and they kept on going until the QC was finally out 2 months later. Okay, at this point they did put a different bottle of reagent on, recalibrated, that fixed it. But when I brought this to the attention of that particular supervisor, he says, I'm going to pay more attention to the median report from now on. Finally, here we have plots for 4 instruments. Yeah, there's 5 on the right-hand side, but the last one is an artifact of the software. 2 instruments running a median of about 9.6 and 2 more running about 9.2. Is there something the matter with 2 instruments? Why don't they agree with each other? They're in the same hospital. Well, it just happens that the high ones are mostly used for outpatients and the low ones are mostly used for inpatients. So once again, the bottom line, when you're doing this kind of statistical monitoring of lab results, you need to consider the patient population that's going into your statistics. All right, some conclusions and recommendations, and I'll finish. Patient-focused QC can identify problems missed by controls, and of course, controls can identify problems missed by patient-focused QC also. But I like it because they can also answer the question, which is going bad, the controls or the test, because that's a dilemma we often struggle with, and we're not sure which one is the problem. It can be applied to some tests, but not all tests. Like I said, it needs to be a test you run frequently, so it's not going to work for tobramycin. Needs to have a fairly narrow distribution of results, so HCG is not a good candidate. And finally, you'd want to use it on tests where a small change has clinical consequences. In choosing it, in setting up your algorithm, you need to choose the parameters wisely, the number to average, the range of results to include, and the warning limits. And then finally, when you have a failure, you need to troubleshoot it the same way you would troubleshoot a QC failure. It might be an instrument problem, but it also might be just a change in the patient population. And with that, we'll all sit down up here and take questions.
Joe and Sten, as they make their way up, we have microphones in the middle of the room. Again, as you formulate some questions, I want to thank everybody again for sticking around a little extra. I know we started a little bit late. Phil, I'll start off with a question while Sten and Joe get settled here, but have you tried moving averages for other tests and ended up discarding that and not using them?
Actually, we have. We tried them for the lipids, cholesterol, trig, HDL, and we found that there was enough variation in the patient population that was coming through the lab that we couldn't detect the small changes we wanted to in, say, cholesterol, for example, and so it wasn't worth it, so we quit doing those.
Any other questions? We have one.
Yeah, thanks to all the eminent speakers for excellent talks. So my question is, Dr. Litten and Sten, like you showed in your slide, when we select total allowable error selection, so you showed clear criteria for total allowable error selection. So what is your recommendation? Like, should we start with clear or recause biological variable, like desirable or minimum, and then after 6 months we should shift to biological variation, like optimum? Like for you, elaborating further in your slide, like you showed, I think, cholesterol, total allowable error 10%, which is the clear criteria, and bias is, I think, 1.9% and CV 0.9, and your sigma matrix was 9. And suppose you take same CV and same bias and you like apply in unity real-time biological variable optimum, it will come around 4 sigma from 9 sigma. So the like when you are using maybe 1.4s or 1.5s rule with n is equal to 2, so if we use like biological variable optimum, it will come 4 sigma level. So then you have to use like multi-rule with n is equal to 4 maybe. So what is your recommendation, like during startup phase of 6 sigma and after 6 months?
I can tell you what we do. Of course, here, we use the CLIA, and that's where we start for the total allowable errors. But there are some tests we feel the CLIA limits are just too wide. HDLs, calcium are good examples. So we look at Dr. Ricos's her levels, recommended levels, and that's what we try to use. But for the most part, we use the CLIA standards. I don't know if this...
Okay. Well, I can give a more complicated answer. Let me start by saying, of course, in the U.S., CLIA is law, so you have to meet those targets. So you better make sure that you're achieving a very good signal level on those, but if you can, then you certainly have the option of aiming for a smaller target, as Dr. Litten did. With the biologic variation goals, or what's called the RICOS goals, many of those are unachievable. They actually are so small. If we just take, for instance, HbA1c, The RICOS goal is set at 3% total allowable error, and there is no method on the market that can achieve that. So while the RICOS goal provides us lots of information, just as Dr. Bach was saying, you have to choose your analytes carefully. Similarly, you have to choose your goals carefully. We can't just assume there's one source of goals that we go to, that we always go to the RICOS goals and always choose the smallest one possible. We have to make sure that the RICOS goal is practical, achievable, realistic. And then to make this even more complicated, there was a meeting in Milan last November where the IFCC convened a task force that will actually overhaul the RICOS goals. They are going through all the data that was used to calculate the RICOS goals and believes that some of that data is no longer valid. So they're going to recalculate those goals over the next few years, and those goals might become even tighter because we're going to start excluding older data sets, older studies that were conducted on older instruments that had more imprecision, so the biologic variation probably looked bigger than it is. As a result, I expect to see more and more RICOS goals to get very small and unachievable. So I think we're going to have to move towards a reality where we understand there are multiple sources of goals, but there's no one source that we should go to. There's no one that's going to achieve a primacy, that it's always going to be the one we go to that's got the best goals. I suppose my father and I have an ambition to try and pick out a set of goals that we will specifically call Six Sigma goals, where we balance what goals are out there with the idea we're going to give you a target that we think you should achieve Six Sigma at, not a target that's so small you're never going to achieve a high level of quality, not a target that's so wide everybody is going to achieve Six Sigma, but one that is challenging, demanding enough to force manufacturers to improve their quality, but still achievable.
But don't you feel CLIA is too loose or too huge, the CLIA goals are? Like suppose, for example, cholesterol is 10%, and if you consider NCP recommendation 3% bias, 3% CV, so the sigma metrics will be around 2.33. So it will be...
Right, well, that's actually the opposite direction. I mean, that's actually saying if you would go that the cholesterol goal is actually like too tight, because the NCP recommendation applying the CLIA goal is below 3 sigma. So if we follow NCEP recommendations, we can't even achieve 3 sigma given the CLIA quality requirement. But definitely, I understand, and we have essentially co-opted the CLIA goals. When the CLIA goals came out several decades ago, they really were only maybe 2 SD goals or 3 SD goals. There were 2 sigma limits, 3 sigma limits. And now what we've actually said is, well, instead of trying to fit 2 SDs in there, we want to fit in 6 SDs. We turn them into 6 sigma goals. So they might look like they're big, but we're trying to hit the very center of the bullseye of that target. We're being much more demanding on the achievement level that we want out of that target.
And I think we're succeeding pretty well in those cases.
Mm-hmm. Yeah.
Just to add one thing, some of our goals come straight from CLIA, but some also come from clinician expectations. I mentioned that 2 millimole per liter sodium target that the ICU docs wrote, and they asked if we could meet it, and I said, we'll do our best.
Dr. Bach, curious about your N values. Like you showed, like the impact of outpatients, which affects like total protein and maybe albumins as well, if you look at those. So wouldn't it be more prudent maybe to use a larger N value?
Well, statistically it would, yes. The problem is it would take so long for me to get a warning when something went bad. So you can't, you have to do an N that doesn't take several weeks to achieve, or even a day or so.
But probably in your main lab, you're probably generating several
Several
average
hundred.
points actually between QC events, aren't you then?
Oh, very much, absolutely.
Okay.
But I mean, I could use an N of 1,000 or even more if I worked at Quest, where they were running 20,000 total proteins a night. But as it stands, that's about as big an N as I can tolerate and still get a reasonably timely alert to a problem. It's a trade-off. You just have to play with it. Okay.
Well, I know it's late, so we're going to take one final question. Dr. Wunderling, do you have a question?
Hey, Dr. Bach, that was an excellent presentation, and again, Sten and Dr. Litten, great presentation. I just have a quick question. So you're doing moving averages. I've seen other labs do continuous monitoring of even sigma metrics every month, every quarter. So I know you said with moving averages, there are assays that may not fit the pictures. There are some that will work with moving averages. So do you plan to do continuous monitoring of sigma metrics as well, or is there plans for that?
That was actually a question I thought I'd ask Sten. If I do a sigma-metric calculation now, it's a snapshot in time. And next time I calibrate that assay or the next lot of reagent I get, my bias is not necessarily going to be the same, which means my sigma-metric is going to be different. How do people do a time average metric somehow? Is there a way to do that?
Well, I actually think this is a better question for Joe.
Oh.
What I've been looking at, of course, everyone probably looks at your monthly summaries. What I wanted to do was look at it over a 3-month period, and that way I was getting at least 100 data points or more for all the assays. And it gave me a snapshot. It gives me a good snapshot of like lot-to-lot changes, calibration changes, and see where the deviation. Generally speaking, we see higher CVs when we go longer because there are certain time periods where you do really well, and then you have short terms where they're really high, maybe for a week or two, but then over a 3-month period it averages out. I feel like it gives us a better snapshot of 3 months. It gives me a better feel for how well the instruments are doing over that period. Versus maybe a shorter term of a month. Even though I look at the month data, but also every quarter sit down and look at the 3 months data. And I learned some things. I see where changes in lot numbers or changes in calibration does have an effect on our results. So it's kind of like a moving average thing in a way, except we're using QC.
Right. You're following something else that's moving.
Yes.
Yeah.
And I would just add that in addition to looking at having seen years of Joe's data, and there's an incredible consistency in the sigma metrics that a Six Sigma assay tends to remain Six Sigma over many, many years. You don't see a huge amount of fluctuation. Numerically, you might see, it says it's 8, it says it's 9, 7.5, but really the way we use a sigma metric, those small differences are not functionally useful. Once it is above 6, it gets one kind of QC, and any difference, any fluctuation, doesn't actually change how you're going to do QC. So it allows you, really all you need to see is it's staying in the same category. Or if you're talking about that method decision chart, does it stay within the same zone? Then it gets the same kind of QC, and you can allow it to drift. You can allow a certain amount of variation to be seen.
Well, thank you very much. I think we're going to conclude the workshop. The speakers will still be available if anybody would like to join and ask additional questions, but please feel free to join us. I have the PACE information up here for anybody that needs it. Please also fill out the questionnaires. But on behalf of Abbott Diagnostics, I would like to thank the 3 speakers for 3 excellent presentations, and thank you for your attention and for attending today's workshop. Please feel free to join us for some refreshments, and Sheila, I hope you open up the bar out there. So thank you very much, everybody, for attending. Enjoy the rest of your week.